There are 4 points of light that orbit Jupiter, easy enough to find with almost any small telescope, even from somewhere as ordinary as a backyard. They sit close to the planet, arranged in a rough line, shifting position from one evening to the next if you watch carefully enough across a few nights. A faint smear of brightness, and then, resolving slowly out of that brightness, 4 separate companions, each one keeping its own quiet distance from the planet they orbit. 3 of those 4 points get talked about constantly. Documentaries are built around them. Spacecraft are sent for them, one at a time, at a cost of billions of dollars. The 4th one, almost never, not because it is small and not because it is faint. It is, in fact, close to the size of an actual planet, near enough in diameter to Mercury that if the 2 worlds were set side by side, you might struggle to say which one had spent its whole existence circling the sun and which one had spent that same span out circling something else entirely. And still, somehow, this one became the point of light that nobody mentions. Not in the documentaries, not in the headlines, barely even in casual conversation, among people who otherwise know a great deal about the outer solar system. Tonight is not about the 3 that usually get the attention. Tonight belongs to the 4th, the one that has been orbiting Jupiter for exactly as long as its siblings, watching everything happen around it, without ever doing anything that looked, from a distance, like very much at all. Its name is Callisto. That name will not carry much weight yet. For a long time, it did not carry much weight for the people who studied it either. There were no eruptions to film, no hidden ocean promising the possibility of life, not at first, no record-breaking size to put in a headline, only a very old, heavily marked world, going around a much louder planet year after year, century after century, offering almost nothing that looked, on the surface, like news. We are going to spend some time with it tonight, not chasing a sudden twist and not building towards some shocking reveal. Just the slower work of paying close attention to something that has been sitting in plain view for over 400 years, mostly overlooked, and finding out what all that stillness has actually been holding on to the entire time. There is, it turns out, a reason this particular silence is worth breaking, and it has very little to do with drama, and everything to do with what drama tends to destroy. If unhurried journeys like this one tend to ease you towards sleep, you are welcome to stay exactly as long as you like tonight, and let the rest of the evening take care of itself from here. We begin. On the 7th night of January in the year 1610, in a city in northern Italy, a man named Galileo Galilei pointed a homemade instrument made of 2 lenses and a wooden tube toward the planet Jupiter, and noticed something he had not expected to see. 3 small points of light sat close to the planet, arranged in a line faint enough that an ordinary eye would have missed them completely. He assumed at first that they were simply stars, distant background stars that happened to fall near Jupiter's path that particular evening. Nothing more unusual than that. But the next night, he looked again, out of habit more than expectation, and the 3 points had moved. Not the way stars move, slowly and predictably across an entire season. They had shifted position relative to Jupiter itself in a single day, as though something about their relationship to the planet had quietly rearranged itself overnight. He kept watching. Night after night, whenever the sky allowed it, returning to the same patch of darkness with the same simple instrument, recording what he saw in careful sketches that still survive. Centuries earlier, long before any of this had a name or a telescope to find it, astronomers in Babylon were already tracking Jupiter's path across the night sky, recording its position month after month on clay tablets, reading meaning into its slow drift through one constellation after another. They watched the planet itself for years at a time, patiently, without instruments of any kind. They had no reason to suspect that 4 small companions traveled alongside it, hidden in its glare, waiting on the edge of visibility for a tool that would not exist for another 2,000 years. A 4th point appeared within the week. The pattern held. Whatever these 4 lights were, they stayed near Jupiter, always near Jupiter, shifting back and forth around it. The the way nothing in the accepted picture of the universe was supposed to shift around anything other than the Earth. For close to 2,000 years, the working assumption in most of the world had been that everything in the sky circled a single fixed center, and that center was the ground beneath every observer's feet. Stars, planets, the sun itself, all of it, turning obediently around one motionless world. Galileo's 4 small lights did not care about that assumption. They orbited Jupiter, plainly, repeatedly, on consecutive nights that left very little room for alternative explanation. It is worth sitting for a moment with what that meant. For one person, on one ordinary winter evening, looking through a tube he had built with his own hands, he was not trying to overturn a worldview. He was trying to understand 4 small lights that refused to behave the way the sky had always behaved before. A few decades before that night, a Polish astronomer named Nicolaus Copernicus had already proposed that the Earth itself moved around the sun, rather than sitting fixed at the center of everything. The idea remained controversial, resisted by much of the scientific and religious establishment of the time. Galileo's 4 small lights did not settle that argument on their own, but they removed one of its oldest assumptions. If objects could orbit a body other than Earth, then Earth's claim to being the single center of all motion in the universe could no longer be taken for granted. Within months, Galileo published his observations in a short book called Sidereus Nuncius, the Starry Messenger, describing what his instrument had revealed. The 4 points of light, the mountains he had also seen on the surface of the moon, the sheer number of stars invisible to the naked eye, that suddenly became visible through glass. None of it on its own proved the new model of the universe correct. All of it, taken together, made the old model far harder to defend. A German astronomer named Simon Marius, working independently and possibly observing the same 4 points around the same period, later proposed the names history settled on. Names borrowed from old stories, figures connected in various ways to the god Zeus, Io, Europa, Ganymede, Callisto. 4 names drawn from the same myth, given to 4 worlds that would turn out to have almost nothing else in common. There is something worth holding on to in the fact that long before any of this had a name, long before any telescope existed at all, people were already looking at this exact stretch of sky. A farmer finishing a late evening's work might have glanced upward toward Jupiter without any instrument at all, seeing only a single steady point of brightness, never suspecting that 4 smaller companions traveled with it, hidden just beyond what an unaided eye could resolve. The planet itself has always been there for anyone willing to look. What changed on that night in 1610 was not the sky. It was the level of attention someone finally brought to it. That distinction matters more than it might seem to at first. The 4 moons were never secret. They were simply too faint, too close to an overwhelming source of light for centuries of careful observers to notice them without help. Sometimes the thing nobody has found yet is not hidden in some far corner of the universe. Sometimes it has been sitting in plain view the entire time, waiting for someone to look just a little more closely than anyone had thought to before. That waiting is where this story actually begins. Not with Callisto specifically, not yet, but with the simple fact that 4 small worlds had been circling Jupiter for billions of years before anyone on Earth knew to count them. 3 of those 4 would go on to become some of the most studied objects beyond our own planet. Spacecraft would be built around them. Entire missions, entire careers, would orbit their discoveries the way the moons themselves orbit Jupiter. The 4th would take a different path, quieter, slower, easier to set aside. But on that first night, none of that division existed yet. There were simply 4 points of light, equally faint, equally new, equally unexplained. For one brief moment in the history of looking upward, all 4 of them mattered exactly the same amount. Galileo himself could not have predicted which moon would end up famous and which would end up nearly forgotten. He recorded their positions with the same careful hand for each one, made no distinction in his notebooks between the moon that would one day be called a volcanic world and the one that would simply be called old. To him, in that winter, they were 4 unexplained points of light, and nothing more needed to be said about any of them yet. That evenness did not last. It rarely does. 3 of the 4 moons started pulling away from the average almost immediately, though not for reasons anyone could have predicted on that first winter night. The pulling away happened slowly, across centuries of better instruments and closer looks, but it happened in 3 distinct directions, and each direction had a name attached to it. Ganymede took the title of largest moon in the solar system, and it has never given that title up. It is bigger across than the planet Mercury, though it carries less mass, built mostly from a mixture of rock and ice rather than Mercury's dense metallic core. Beneath its surface, something deep inside Ganymede appears to be moving in slow, sustained patterns, generating a magnetic field of its own, the only moon known to do that anywhere in the solar system. A compass carried to its surface would actually point somewhere, the way one does on Earth, which is not true of any other moon we have ever studied. Its surface tells 2 different stories at once. Older, heavily marked terrain sits beside younger regions carved with long parallel grooves, evidence that something inside this moon reshaped large portions of its own face at some point in the deep past, erasing whatever record of early bombardment those grooved regions once held. Observations using the Hubble Space Telescope, studying faint patterns in Ganymede's thin atmosphere, have added to the case that an ocean of liquid water sits buried somewhere inside, sandwiched between layers of ice under enough pressure to behave in ways ordinary ice never does on the surface of our own planet. Roughly 2/3 of Ganymede's surface carries that younger, reshaped character. Only the remaining third still holds anything close to its original face. Europa took a different path toward attention. Its surface is some of the smoothest and youngest found on any solid body we have studied. A shell of frozen water with very few impact scars, as though the ice keeps quietly repairing itself. Cracks and ridges cross that shell in patterns that suggest motion underneath, something shifting, breaking and refreezing again and again over a very long span of time. A spacecraft named Galileo, which spent 8 years orbiting Jupiter through the 1990s, detected a magnetic signal at Europa consistent with a layer of salty liquid water hidden beneath all that ice, possibly holding more water than every ocean on Earth combined. That single signal reshaped an entire field of study almost overnight. A mission called Europa Clipper, carrying a price tag near $5 billion, left Earth in 2024 and is currently on its way to test whether that hidden ocean could actually support life. Once it arrives, sometime around the year 2030, it will carry out dozens of close passes over the icy shell, measuring the thickness of the ice, sampling whatever thin atmosphere clings to the surface, and watching for any sign that material from below ever finds its way up through the cracks. Of all the questions planetary science is currently capable of asking, very few carry the weight of this particular one, whether life, in some form, might already exist somewhere else in our own solar system, not in the distant past, but right now, hidden beneath a shell of ice. Io took the most immediate path of all, the one that needs no instrument and no patient analysis to notice. It is the most volcanically active body anywhere in the solar system, not just among moons, but among everything we have ever observed. Hundreds of eruptions occur across its surface at any given moment, fed by enormous tidal forces. As Io moves through its orbit, the combined pull of Jupiter and its neighboring moons flexes the entire body over and over, heating its interior until rock itself begins to melt. Plumes of sulfur rise hundreds of kilometers above the surface in some of these eruptions, arcing through empty space before settling back down as a fine frost that paints the ground in shades of yellow, orange, and deep red. The surface barely holds still long enough to be mapped properly. Impact craters almost never survive there, buried under fresh material within a few million years of forming, a blink of an eye by the standards of anything else nearby. These 4 moons, taken together, carry a name of their own. Astronomers call them the Galilean moons, after the man who first sketched them, and for centuries afterward, They served a purpose that had nothing to do with volcanoes or oceans or magnetic fields at all. Sailors and surveyors used the timing of their eclipses, the moments each moon slipped briefly into Jupiter's shadow, as a kind of clock visible from almost anywhere on Earth, useful for working out longitude long before reliable mechanical clocks existed at sea. In 1676, a Danish astronomer named Ole Rømer noticed something odd in those eclipse timings. Io kept slipping into Jupiter's shadow a little later than predicted when Earth was farther from Jupiter in its orbit, and a little earlier when Earth was closer. The difference was small but consistent, and Rømer eventually proposed the only explanation that fit. Light itself was not instantaneous. It took time to cross the additional distance, and that travel time was shut up as a delay in exactly when a small moon appeared to vanish into shadow hundreds of millions of kilometers away. It was the first time anyone had measured the speed of light using nothing more than careful, patient timing of something most people would have dismissed as a minor technical curiosity. There is a reason all three of these moons behave the way they do, and the reason has very little to do with luck. Io, Europa, and Ganymede are locked together in a precise gravitational relationship, completing their orbits around Jupiter in a fixed ratio relative to one another. Every time Ganymede completes a single orbit, Europa completes exactly 2, and Io completes exactly 4. Picture 3 dancers on a stage, each tracing a different sized circle, but timed so precisely that every 4th step of the smallest dancer lines up exactly with every 2nd step of the middle one and every single step of the largest. None of them can drift out of that pattern even slightly without the other 2 pulling them back into place. That is, in effect, what gravity is doing to these 3 moons continuously every single day, and has been doing for longer than there has been any dancer or any stage to compare it to. That repeating pattern keeps tugging on all 3 moons in a continuous rhythm, flexing their interiors again and again, generating heat that never quite has the chance to fade before the next tug arrives. Volcanism on Io, a flexing ice shell over an ocean on Europa, enough internal warmth to drive a magnetic field on Ganymede. 3 very different outcomes, all powered by the same underlying mechanism, the same shared rhythm. 3 moons locked into a dance that none of them ever agreed to and none of them can leave. 1 moon sits outside that arrangement entirely. Right now, as you are listening to this, sunlight that left the sun roughly 43 minutes ago is still completing its journey toward Jupiter and everything orbiting it, including a 4th moon that takes no part in the rhythm shared by its 3 siblings. That light will reach Jupiter's outermost large moon a few minutes after it reaches the others. Traveling the same distance, it has traveled every single day for longer than there has been anyone present to notice it arriving. It will fall on volcanic plains still cooling from an eruption that happened hours ago. It will fall on ice fractured sometime in the last few centuries by motion deep below. It will fall on a magnetic field generated by something still stirring slowly far beneath a frozen crust. And then it will fall on a 4th surface entirely, a much older one that has not been meaningfully rearranged by anything happening underneath it in longer than human history has existed to measure it. This 4th moon orbits much farther out than the other 3, nearly 2 million kilometers from Jupiter, completing a single lap around the planet roughly every 17 days, well beyond the reach of its siblings' shared gravitational rhythm. No precise ratio links its orbit to anything nearby. No repeating tug flexes its interior on a fixed schedule. Whatever heat it generated in its early history has had nothing renewing it since. No outside rhythm reaching in to stir things up again. Its name, as you already know by now, is Callisto, and on paper, it should not be the overlooked one. It ranks 3rd largest among all the moons in the solar system, smaller only than Ganymede and a single moon belonging to Saturn. Its diameter sits close enough to that of Mercury that the 2 worlds, set beside one another, would be difficult to tell apart at a glance. Built from roughly equal parts rock and ice, it carries a fraction of Mercury's mass, but in raw size alone, it would outrank Pluto, Eris, and every other dwarf planet ever classified, along with every object in the asteroid belt combined. If it happened to orbit the Sun on its own, instead of circling a much larger planet, it has been part of the same four-moon family since the very first night anyone noticed any of them. It carries one of the same four mythological names, drawn from the same old stories, given equal weight in Galileo's earliest sketches, recorded with the same careful hand as the moon that would one day be famous for fire, and the one that would one day be famous for water, and the one that would one day be famous for sheer size. And yet, somehow, across 4 centuries of growing attention toward its 3 siblings, this particular moon kept slipping toward the edges of the conversation. Mentioned last, if it was mentioned at all, described, more than once, in terms that suggested very little was happening there worth describing. A name people half remember from a documentary about somewhere else. That description turns out to be almost entirely wrong, but understanding why requires looking carefully at exactly what staying outside that shared rhythm actually did to a world this size. Over a span of time, most of us are not built to imagine clearly. When spacecraft finally returned the first close images of this moon in the late 1970s, what came back looked, at first glance, like very little at all. A pale, grey-brown sphere, covered from one horizon to the other, in circular marks of every size, with no obvious colour, no visible motion, nothing that resembled the fire of one sibling, or the ice fractures of another, or the magnetic drama of the third. The scientists studying those first images were not unkind about it, exactly. They were simply unmoved, just craters. An overwhelming, almost monotonous number of craters, layered over craters, stretching across the entire visible surface. It is where the story turns next, toward that surface, and toward what an entire moon covered in nothing but old wounds actually turns out to mean. A crater, on its own, does not say very much. It says an object struck a surface once, at some point in the past, and left a mark behind. A surface entirely covered in craters says something else. It says nothing has happened here for a very long time, except objects striking it from above. The first close look came from 2 spacecraft, Voyager 1 and Voyager 2, passing through the Jovian system in 1979 on their way toward the outer solar system. Their cameras returned images of all 4 large moons during those brief flybys. Each frame radioed back across hundreds of millions of kilometers and pieced together, line by line, into pictures nobody on Earth had ever seen before. The images of Callisto showed exactly what its reputation would later rest on. Craters, layered over craters, in every direction the cameras pointed. 16 years later, a spacecraft simply named Galileo settled into orbit around Jupiter itself, spending the better part of a decade making repeated close passes by all 4 large moons, gathering far sharper images and far more detailed measurements than 2 brief flybys ever could. It was Galileo's cameras circling back to Callisto again and again between 1995 and 2003 that first revealed the surface in the kind of detail needed to notice the subtler patterns, the shift from simple bowls to central peaks, to central pits. As craters grew larger, the dark coating thickening unevenly across different regions, the full extent of the 2 great ring systems that earlier images had only hinted at. Callisto's surface belongs to that second category, more completely than almost anywhere else humans have ever managed to photograph. Every visible patch of ground carries the marks of impact. Large circles overlapping medium circles, overlapping smaller circles, the rims of the oldest ones worn down, almost to nothing, by everything that has landed on top of them since. Planetary scientists have a specific term for a surface in this condition. They call it saturated. A surface reaches saturation once it has absorbed so many impacts that there is no longer any truly empty ground left to strike. From that point forward, every new impact does not simply add a fresh mark, it erases part of an older one to make room for itself. Think of a single sheet of paper struck again and again by the same pen for longer than any of us can easily picture. At first, each new mark lands on clean space. Eventually, there is no clean space left, and every additional mark can only land on top of something already written there, smudging part of it away to make its own small claim on the page. Callisto reached that condition a very long time ago, more completely than any other large body in the solar system we have managed to study closely. Once a surface saturates, counting craters stops being a reliable clock in the ordinary sense. A surface that saturated 3 billion years ago can look at a glance almost identical to one that saturated 4 billion years ago, because the page, in both cases, is simply full. Working out exactly how old Callisto's terrain is requires comparing its largest, slowest forming features against similar records elsewhere, rather than a simple count of every crater in view. The best current estimates place its oldest visible terrain at somewhere close to 4 billion years, reaching back almost to the very beginning of the solar system itself. No other large body of comparable size has held onto a record this old, this completely. Earth's surface recycles itself constantly through the slow churn of its crust. Venus appears to have been resurfaced in one or more dramatic episodes that erased almost everything that came before. Our own moon kept its oldest highlands, but lost large stretches to ancient floods of dark volcanic rock that filled in low ground and buried whatever craters had formed there first. Ganymede, Callisto's nearest twin in size, lost roughly 2/3 of its own early surface to the same kind of internal reshaping. Callisto lost none of it, and the reason traces directly back to its position outside the gravitational rhythm shared by its 3 siblings. Without that shared rhythm tugging on it, flexing its interior again and again the way it does for Io, Europa, and Ganymede, Callisto never generated the kind of sustained internal heat that drives volcanic eruptions or cracks a crust apart from below. Whatever warmth its interior held in the earliest days after formation had nothing renewing it. No tidal engine reached in from outside to keep it going. Over time, that early heat simply faded, and once it faded, nothing remained capable of erasing or rearranging the surface above it. No eruptions to bury old craters under fresh material. No internal pressure to fracture the crust and expose anything new underneath. Churning, no folding, no resurfacing of any kind. Just a slow, steady accumulation of impacts, one on top of another, across the entire span of solar system history, with nothing internal ever stepping in to interrupt the process. This is where the description of Callisto as somehow uneventful begins to fall apart. The absence of internal activity did not leave the surface empty of information. It left the surface as close to a complete, unedited record as anything this size is ever likely to offer. Look closely enough at that record, and the craters themselves stop looking the same. The smallest ones, generally under about 5 kilometers across, tend to keep a simple rounded bowl shape, the kind produced when a relatively small impact compresses and excavates material without enough energy left over to do much else. Move up into craters between roughly 5 and 40 kilometers across, and a different feature starts appearing at their centers. A peak formed in the instant after impact, when material compressed at the bottom of the newly formed crater rebounds upward before settling, the way a struck surface sometimes springs back rather than simply staying dented. Larger still, somewhere between 25 and 100 kilometers across, the central peaks give way to something else entirely, a pit rather than a peak, sitting at the center of the crater floor. This particular feature does not appear on rocky worlds under ordinary conditions. It seems to require a target made partly of ice, where the violence of impact can momentarily mobilize volatile material trapped within the crust, material that briefly behaves almost like a fluid before settling back into solid form, leaving a depression rather than a raised dome where the center of the crater should otherwise be. Above roughly 60 kilometers in diameter, a third pattern sometimes appears, a dome rather than a pit or a peak, interpreted as the result of deeper material being pushed upward during the slow collapse that follows the most energetic impacts, material rising from far enough below the surface to behave differently than anything closer to the top. There is a second clock hidden in these craters too, slower and far less precise than crater counting, but useful in its own way. The sharpest, freshest rims soften gradually over time, worn down not by wind or water, since Callisto has neither, but by the slow escape of ice through sublimation, and by the endless patter of micrometeorites, too small to leave craters of their own, each one chipping away, an almost immeasurable amount of material from whatever rim happens to stand in its path. A crater's degree of softening, set alongside its size and its position, relative to everything around it, adds one more thread to the larger pattern. Researchers are slowly piecing back together. None of this is decorative variation. Each shift from peak to pit to dome traces a change in the physical properties of the material an impact happens to strike. At increasing depth below the surface, cold, rigid material near the top behaves one way under sudden violence. Warmer, weaker material, somewhat deeper, behaves another way entirely. Part of the explanation comes down to the simple fact that ice is not rock. On the Moon or on Mercury, decades of studying impacts into solid stone have produced a well-tested set of rules connecting the size and speed of an impactor to the shape of the crater it leaves behind. Callisto's crust is not solid stone. It is a mixture of water ice and rocky material, threaded through with pockets where the two never blended cleanly. Ice is lighter than rock, mechanically weaker at the temperatures found on Callisto's surface, and capable of shifting briefly into something closer to a thick fluid under the extreme pressure of a high-speed impact, before settling back into solid form within moments. A collision energetic enough mobilizes that icy material in ways solid rock never would, and the resulting crater carries the signature of that difference, written directly into its shape. By studying exactly where each kind of crater tends to appear, and at what size the transition from one type to another tends to occur, researchers can begin to sketch a rough picture of conditions inside Callisto's crust, layer by layer, without ever having to drill into it directly. A peak at the center of a 40-kilometer crater might rise several hundred meters above the surrounding floor, a small mountain raised in an instant by the rebound of compressed material below. A pit at the center of an 80-kilometer crater might sink a comparable distance the opposite direction, a depression left behind where ice briefly flowed rather than shattered. Different processes recorded in the same patient language of shape and depth. Every individual scar, in other words, is also a small instrument, recording something about the material it happened to strike, in addition to recording the impact itself. There is a particular kind of patience required to read a record like this one. In certain old lighthouses, the keepers who once tended them left behind logbooks meant to be filled in every single night without exception, regardless of weather, regardless of whether any ship ever passed close enough to matter. Generation after generation of keepers added their entries to the same unbroken record, each one trusting that the page would still be there for whoever came next, never imagining that anyone, centuries later, might sit down and read the entire thing from the very first entry to the very last, looking not for any single night, but for the shape of the whole pattern across all of them at once. Reading Callisto's surface asks for something close to that same kind of patience. Nothing on it was written quickly, and nothing about understanding it can be rushed either. Every mark sits exactly where it landed, in the order it arrived, layer beneath layer, for anyone willing to look closely enough and slowly enough to follow the record all the way back toward where it began. Callisto's surface holds one more layer worth noticing before turning to its largest and oldest scars. Across the smallest scales, something appears to be missing entirely. Spacecraft images show far fewer tiny craters, below roughly a kilometer across, than bombardment models predict should be sitting there. Instead, the surface at that scale looks softened, smoothed, as though a thin blanket has settled gently over the underlying terrain and worn away its sharpest edges. That blanket is real, though it is not made of anything that fell from above. Over billions of years, sunlight and charged particles streaming from Jupiter's surrounding environment have slowly stripped water ice directly from Callisto's surface, through a process called sublimation, where solid ice converts straight into vapor without ever passing through a liquid stage and drifts away into space. What remains behind is whatever was not ice to begin with. Dark grains of rock and carbon-rich material, left behind grain by grain as their icy surroundings slowly disappeared around them, gradually thickening into a fine, dark residue that coats the original surface like a layer of dust, settling undisturbed across the floor of a room nobody enters anymore. Above that darkened surface, Callisto holds the barest trace of an atmosphere, so thin that calling it an atmosphere at all stretches the word close to its limit. Mostly carbon dioxide, at a pressure measured in trillionths of the pressure found at Earth's surface. It amounts to little more than a whisper of gas, likely sustained by the same slow release of trapped material that thickens the dark surface coating, drifting away into space almost as quickly as it forms. Surface temperatures swing from somewhere around minus 130 degrees Celsius in full sunlight to far colder still on the night side, cold enough that little about the surface changes from 1 hour to the next or 1 century to the next in any way an instrument could easily detect. This residue explains something that puzzled the earliest researchers studying Callisto. Despite containing a substantial amount of water ice, much like its siblings, Callisto reflects only about 22% of the sunlight that reaches it. Europa, by comparison, reflects roughly 67%, its surface kept bright by continuous renewal. Ganymede sits in between, near 43%, its mixture of old and young terrain, producing a mixture of dark and bright ground. Callisto sits at the bottom of that scale, not because it lacks ice, but because billions of years of undisturbed exposure have buried whatever ice remains beneath a coating. Its siblings never had the chance to accumulate, their surfaces too frequently renewed for any comparable layer to build up and stay. Fresh impacts occasionally punch straight through that dark coating, exposing cleaner ice from just beneath the surface, and for a while, those impact sites stand out as noticeably brighter patches against the surrounding darkness, before the same slow process begins quietly working on them too, gradually returning them to the same muted tone as everything around them. Measurements of the light reflecting from those brighter patches confirm what the pattern already suggests. The signature of water ice shows up clearly in their spectra, far more clearly than in the darker terrain surrounding them, exactly as expected if the bulk of Callisto's crust remains genuinely icy underneath, and only its outermost surface, exposed for billions of years to sunlight and radiation, has slowly darkened from the buildup of everything left behind once the ice itself drifted away. The darkness, in other words, is not a sign of different composition. It is a sign of age, accumulated one imperceptible layer at a time, year after year, for longer than there has been any observer present to watch it happen. The pace of that accumulation is almost impossible to picture clearly. In any given year, only the thinnest imaginable layer of surface ice converts to vapor and drifts away, leaving behind an even thinner trace of dark residue. Multiply that by a few billion years, and the modest blanket now covering Callisto's surface is the result, grain settling on grain, far too slowly for anything to register as motion, fast enough, given enough time, to lower an entire moon's reflectivity by more than half. All of this, the saturation, the crater types, the dark coating, plays out across a surface marked by two features so large that calling them simply craters understates what they actually are. The larger of the two carries the name Valhalla. At its center sits a brighter region, roughly 600 kilometers across, surrounded by ring after concentric ring of fractured terrain extending outward to a total diameter of something close to 3,000 kilometers. Standing at the very center of that structure and looking outward in any direction, the rings would stretch beyond the horizon before reaching their outer edge, a single impact scar wide enough to swallow a significant fraction of an entire continent. An object likely tens of kilometers across struck Callisto here, early in its history, at a speed measured in tens of kilometers per second. The shock from that collision did not simply punch a hole. It propagated outward through the icy crust in concentric waves, fracturing the surface into the ring pattern still visible today. The way ripples spread outward from a single point dropped into still water, except frozen permanently into solid ground rather than fading away within seconds. It is difficult to hold the actual scale of that event in mind for very long. A ring system close to 3,000 kilometers across is wider than the distance separating many of Earth's capital cities from one another. Standing anywhere near the center of Valhalla in the moments after it formed, an observer would have seen the ground itself rearranged in a single event across an area larger than most countries, the entire structure locked into its current shape within minutes and left almost entirely untouched ever since. A second structure, somewhat smaller, carries the name Asgard, measuring close to 1,600 kilometers across, built from the same basic pattern of a bright central zone surrounded by concentric rings, though less extensive and more worn down by everything that has struck it since. Together, Valhalla and Asgard stand as the clearest proof that Callisto experienced at least 2 collisions of genuinely enormous scale during its early history, each one energetic enough to fracture the crust across distances usually reserved for entire continents, and each one preserved well enough, all this time later, for scientists to still measure the spacing of their rings and draw conclusions from it. On a world with any meaningful internal activity, structures this size would not have survived intact for long, geologically speaking. A few 100 million years of tectonic motion, volcanic flooding, or large-scale resurfacing would have been more than enough to soften, bury, or completely erase features on this scale. Earth's plate tectonics would have dismantled something this large within a single cycle of crustal motion. Even on Ganymede, the formation of younger groove terrain disrupted and partially destroyed several of that moon's own oldest, largest impact scars. On Callisto, both structures remain largely intact, worn only by the slow accumulation of smaller impacts layering on top of them since, and by an extremely gradual softening of their sharpest edges over immense stretches of time. Nothing internal ever stepped in to interrupt either record. They simply sat there, accumulating detail rather than losing it, for roughly as long as the solar system itself has existed. Structures this size matter for a reason beyond their scale alone. Smaller craters are useful for statistics, for working out general patterns in bombardment over time, but the very largest impacts mark the upper limit of how energetic any single collision in this region of space ever became, and Callisto holds 2 of the clearest examples of that upper limit still visible anywhere in the solar system. Counting craters carefully across Callisto's surface, sorting them by size, and comparing the resulting pattern against a similar count from the Moon reveals something unexpected. The 2 records do not match. Callisto's surface shows proportionally fewer small craters than the lunar pattern would predict, particularly at sizes below about 10 kilometers across, even after accounting for differences in surface age between the 2 worlds. That mismatch carries real weight. The Moon's crater record has been calibrated against actual rock samples, brought back to Earth by the Apollo astronauts and dated directly in laboratories, using the slow, steady decay of radioactive elements locked inside them. Matching those precise ages to the crater density measured on the same patches of lunar ground give scientists a reliable link between how crowded a surface is with craters and how old that surface actually is. That calibration reflects the population of objects that struck the inner solar system across its history, dominated by asteroids, gradually nudged out of the main belt between Mars and Jupiter, and sent on paths that eventually crossed the orbits of the inner planets and their single large moon. The method itself is fairly simple to describe, even if the work behind it took decades. Sort every crater on a surface by size. Count how many fall into each size range. The resulting pattern, plotted as a curve, is not random. A population of impactors weighted towards small objects produces a steep curve, crowded with small craters relative to large ones. A population weighted slightly more toward larger objects produces a flatter curve. The shape of that curve becomes a kind of fingerprint, tracing back to whatever was doing the striking in the first place. Callisto orbits much farther out, in a different neighborhood entirely, and the objects striking it appear to come from a different source population. Comets, drifting in from far beyond Jupiter, accelerated to tremendous speed by the planet's gravity as they fall inward, carry a different size distribution than asteroids do, generally producing fewer small fragments relative to large ones. That difference shows up directly in the crater record. Callisto has been quietly keeping for 4 billion years, a record no body in the inner solar system is positioned to hold, because the inner planets and the Moon simply do not see enough of this particular population of impactors to register their signature clearly. In other words, Callisto's cratered surface is not only a record of impacts in general, it is, more specifically, one of the clearest surviving records anywhere of what has been falling through the outer solar system since its earliest days, a record kept intact for exactly as long as nothing internal interfered with it. That record touches on a question planetary scientists have debated for decades, often referred to as the late heavy bombardment. Evidence from lunar samples suggests that roughly 700 million years after the solar system formed, the inner planets experienced a noticeable spike in impacts, possibly triggered by a slow rearrangement in the orbits of the giant planets. An event that would have sent waves of small bodies scattering inward and outward across the entire solar system at once. If something like that happened, its effects should not have stopped at Mars. They should have reached all the way out to Jupiter's moons as well. Callisto's largest stars, Valhalla and Asgard among them, offer one of the few available ways to test that idea from the outer solar system side of things. Estimating exactly when those two basins formed remains difficult, with current estimates spread across a wide range, but the statistical character of the surrounding crater population, taken as a whole, continues to inform models of whether that ancient bombardment arrived as a single sharp pulse or unfolded more gradually, stretched out across a much longer stretch of time. Either way, the answer is sitting somewhere in that cratered surface, waiting to be read with greater precision than current instruments have yet managed. Ganymede formed from the same basic materials, at roughly the same time, in the same neighborhood around Jupiter, could in principle have preserved a similar record. Instead, whatever internal process reshaped 2/3 of its surface also erased most of its own early bombardment history along the way, leaving only its remaining older terrain, much of it disturbed by proximity to everything reshaped around it, to tell a far less complete version of the same story. That difference matters well beyond Jupiter's own moons. The comets that struck Callisto over billions of years originated far out beyond the giant planets, in reservoirs of icy material left over from the solar system's formation, the same general region now referred to as the Kuiper Belt. Studying the size and frequency of objects drawn from that population, gradually nudged inward over time by the gravity of the giant planets, helps researchers understand how small icy bodies broke apart and evolved across the outer solar system's long history. Questions that connect directly to how planetary systems take shape in general, including systems orbiting other more distant stars. Almost everywhere else capable of preserving that signal in detail has already erased it. Callisto, simply by doing nothing, kept it. There is a kind of trade implied in all of this, though none of these worlds made any actual choice. Ganymede gained a magnetic field, an evolving surface, signs of an ocean layered deep beneath shifting ice. In exchange, it lost most of the deep record of its own early history. Europa gained a smooth, continuously renewed shell and a serious case for hidden habitability, at the cost of losing nearly its entire cratering record to that same constant renewal. Io gained the most violently active surface known anywhere, while losing every trace of any impact older than a few million years beneath constant fresh material. Callisto gained none of that activity. What it kept instead was the original draft intact, written across 4 billion years and never meaningfully edited since, sitting quietly while every world around it traded its own deep past for a more dramatic present. That trade is the reason a moon, nearly the size of a planet, ended up looking, to early observers, like the least interesting of the four. And it is also looked at from a different angle, the precise reason its surface turned out to matter more than almost anyone studying it at first expected. None of these four moons made any choice in the matter. Each outcome traces back to plain physics, to distance from Jupiter, to whether or not a moon happened to sit inside a particular gravitational rhythm during its early history. And yet the language of trading something away for something gained still fits in its own quiet way. A surface that never changes cannot also erupt, or crack open, or generate a magnetic field of its own. Whatever a world becomes, in the long run, it tends to become at the cost of whatever it might otherwise have stayed, because everything visible so far sits on the outside. The craters, the dark coating, the faint trace of atmosphere, the two enormous ring systems, all of it belongs to Callisto's surface, the part any spacecraft can photograph from orbit without needing to go any deeper. The part 4 centuries of careful watching have, by now, mapped in close to its entirety. What sits underneath that ancient, battered crust turns out to be a considerably stranger question, and one that nobody has been able to answer completely, even now. The tool that opens a question like this one is not a camera, it is gravity itself. When a spacecraft passes close to a moon, the moon's own gravity tugs on it, bending its path by an amount too small to notice directly, but precise enough to measure if the tracking is careful enough. Radio signals bounced between the spacecraft and antennas back on Earth can capture that bending in fine enough detail, and from the shape of the bend, scientists can work backward to figure out how mass is distributed inside the body, doing the pulling. A world where heavy material has sunk toward the center, leaving lighter material closer to the surface, bends a passing spacecraft's path differently than a world where everything remains mixed together in roughly the same proportions throughout. The difference is subtle, smaller than almost any everyday measurement most of us encounter, but it is there, written into the geometry of the flyby itself, recoverable from nothing more than the timing of radio signals crossing hundreds of millions of kilometers of empty space. Scientists describe that distribution using something called the moment of inertia factor, a single number that says, in effect, how concentrated a body's mass is toward its middle. A perfectly uniform sphere, with the same density from its core to its surface, carries a value close to 0.4. A body that has fully separated, with dense material sunk into a distinct core and lighter material, risen to form an outer shell, carries a noticeably lower value, typically somewhere between 0.3 and 0.35, depending on how complete that separation turned out to be. A figure skater, pulling their arms in close to their body, spins faster than the same skater with arms held wide, because the same mass, concentrated nearer the center of rotation, behaves differently than mass spread farther out. A planet or moon with its densest material gathered near the core is, in a loose sense, holding its arms in. One with everything mixed together evenly, dense and light material alike, scattered throughout its volume, is holding its arms out wide. The moment of inertia factor is simply a way of measuring, from a distance, which posture a given world has settled into without ever needing to see beneath its surface directly. The Galileo spacecraft measured this value for Callisto during its repeated flybys in the late 1990s. The result came back at approximately 0.355. That number sits in an odd in-between place. It is lower than the value expected for a completely uniform body, which suggests some genuine separation has happened inside Callisto over its long history. But it sits noticeably higher than the value measured for Ganymede, which points toward a body that completed that separation fully, sorting itself cleanly into a metallic core, a rocky layer above it, and an icy shell on top. Callisto, in other words, appears to be caught partway through a process that Ganymede, its near twin in almost every other respect, somehow finished as though two siblings set out on the same long walk and only one of them ever actually arrived. That single fact does not sound, on its own, like much of a puzzle, but sit with what it actually implies for a moment, and the puzzle becomes harder to set aside. Ganymede and Callisto are close to the same size. They carry roughly the same overall density, meaning roughly the same proportion of rock to ice. They formed from the same surrounding disk of material around the young planet Jupiter, at close to the same time, drawing from the same general reservoir of building blocks. By almost any straightforward expectation, two worlds built this similarly, from this similarly, should have followed a similar path afterward. They did not. Researchers sometimes call this puzzle the Ganymede-Callisto dichotomy, a slightly formal name for what is, at its heart, a fairly simple and slightly unsettling observation. Two worlds that should have turned out almost the same somehow did not. The question matters for more than these two moons alone, since understanding why nearly identical starting conditions can lead to such different outcomes touches on how moons, and by extension planets, take shape everywhere, including around stars far beyond our own. Researchers have spent decades proposing explanations for why one moon separated completely, while its near twin stalled partway through, and no single explanation has yet earned full agreement. One early idea pointed to the shared gravitational rhythm linking Io, Europa, and Ganymede. If that rhythm provided Ganymede with an extra ongoing source of internal heat that Callisto, sitting outside the pattern, never received, the difference would have a fairly clean explanation. But the timing complicates that story. Some models suggest the precise rhythm linking those three moons may not have existed, in its current form, during the earliest period when both moons' interiors were hottest and most likely to separate. If the rhythm assembled gradually, over a longer stretch of time, it may have arrived too late to be the deciding factor in whether Ganymede differentiated in the first place, even if it helped sustain activity thereafterward. A second line of thinking looks instead toward the same ancient bombardment discussed earlier, the period roughly 700 million years after the solar system formed, when impacts across the inner planets appear to have spiked sharply. Ganymede orbits closer to Jupiter than Callisto does, and objects falling toward Jupiter pick up additional speed the deeper they fall into its gravity, the way anything gathers speed falling toward a larger mass. A faster impact delivers more energy on arrival, all else being equal, simply because speed itself carries energy. According to this model, the bombardment Ganymede experienced during that ancient spike may have carried just enough extra energy, compared to what reached Callisto farther out, to push its interior past a critical threshold. Once enough rock begins sinking toward the center of a partially molten body, the very act of sinking releases additional gravitational energy as heat, which softens still more material, which allows still more sinking, in a self-reinforcing cycle that once started tends to carry itself through to completion rather than stalling partway. Callisto, absorbing somewhat less energetic impacts at its greater distance from Jupiter, may have warmed enough to begin that same cycle without ever quite crossing the threshold needed to make it self-sustaining, leaving the process to stall out somewhere in the middle, exactly where the gravity measurements now find it. This explanation has its own weaknesses. It depends on assumptions about exactly how intense that ancient bombardment really was and how it was distributed across the two moons, assumptions that remain difficult to pin down precisely from this distance in time. A third, more recent line of research approaches the question from an entirely different angle, looking not at what happened after formation, but at how each moon came together in the first place. A study published in 2025 modeled the possibility that both moons grew primarily by sweeping up small grains of material, sometimes called pebbles, drifting through the disk surrounding young Jupiter, rather than by colliding with larger pre-formed building blocks. Pebble by pebble growth tends to deposit its energy near the surface, where it radiates away into space relatively easily, rather than burying it deep inside, where it would linger and contribute to internal heating. The study found that if Callisto formed primarily through this gentler process, its interior could plausibly have stayed cool enough to avoid full separation, even while Ganymede, forming under slightly different conditions, perhaps closer to the planet, or incorporating a few more substantial impacts along the way, crossed into full differentiation. A closely related idea looks at the question from the opposite direction entirely, asking not what extra energy might have pushed Ganymede over the edge, but what might have kept Callisto from getting there in the first place, despite receiving what should have been, over 4.5 billion years, more than enough radioactive heat to finish the job on its own. One possibility involves convection, the same basic process that stirs a pot of slowly heated soup, with warmer material rising and cooler material sinking in a continuous, gentle circulation. If Callisto's interior convects efficiently enough, that circulation could carry heat outward and let it escape into space before it ever has the chance to accumulate to the point of triggering full separation, acting as a kind of built-in cooling system that quietly prevented the Moon from ever crossing the threshold its twin apparently did cross. Whether the interior actually convects efficiently enough to explain this depends on properties, like the exact stiffness of an ice and rock mixture under enormous pressure that remain difficult to measure from any distance. None of these explanations has displaced the others entirely. Each fits part of the available evidence. Each leaves something unexplained. The honest summary, for now, is that the difference between these two nearly identical moons remains a genuinely open question, one that will likely stay open until a future spacecraft can measure Callisto's interior with far greater precision than Galileo's instruments allowed, and the interior holds a second mystery layered on top of the first. During several of those same close flybys in the late 1990s, Galileo's magnetometer picked up something unexpected near Callisto, a faint disturbance in the local magnetic field, the kind that appears when a planet's own shifting magnetic field induces an electrical current inside a conducting layer hidden somewhere within a nearby moon. That current, in turn, generates its own small magnetic field detectable by a passing spacecraft sensitive enough to notice it. This is the same basic phenomenon that first hinted at Europa's hidden ocean. Jupiter's magnetic field sweeps past these moons continuously as they orbit, and if a moon contains a layer of electrically conductive material beneath its surface, most likely salty liquid water, that sweeping field induces a response that instruments can detect from a distance. The principle resembles, in a rough way, how a simple electric generator works. Move a conductor through a changing magnetic field, and a current begins to flow inside it, with no wires or batteries required, simply as a consequence of the motion and the field interacting. Jupiter's magnetic field is not perfectly steady. It tilts and wobbles slightly as the planet rotates, sweeping past each orbiting moon as a field that changes in strength and direction from one moment to the next. Any sufficiently conductive layer caught inside that sweeping field responds the same way a generator's conductor does, generating a small electrical current, and that current produces its own faint magnetic field in turn, layered on top of everything else a passing spacecraft happens to measure. Salt dissolved in water makes the water considerably more conductive than pure water alone, which is precisely why a salty ocean produces a clearer signal than a layer of plain ice ever would. At Europa, that signal came through strongly and fairly unambiguously. At Callisto, it arrived weak and considerably harder to interpret cleanly, because Callisto carries something Europa does not, a surprisingly dense layer of charged particles in its uppermost atmosphere, called an ionosphere, which is itself electrically conductive and capable of producing a magnetic signal of its own in response to Jupiter's field. Untangling how much of the observed signal came from a possible ocean deep inside, and how much came from that ionosphere much closer to the surface, turned out to be far more difficult than anyone expected at the time. For more than 2 decades afterward, the question sat unresolved. A study published in 2017 argued that the ionosphere alone could plausibly account for a significant share of what Galileo had measured, casting real doubt on the ocean interpretation. The ambiguity persisted, neither confirmed nor ruled out, a loose thread left hanging from one of the most capable missions ever sent to the outer solar system. In early 2025, a research team based at NASA's Jet Propulsion Laboratory revisited the question with a more thorough approach. Rather than relying on a single flyby or a single frequency of Jupiter's driving magnetic field, the team combined data from every available Galileo pass near Callisto, built detailed models of the Moon's variable ionosphere, and tested a very large number of possible interior configurations against the full set of observations at once, systematically varying the depth, thickness, and conductivity of a hypothetical ocean layer alongside the properties of the ionosphere itself, searching for whichever combination explained the data most consistently. Because an ionosphere and a genuine subsurface ocean respond somewhat differently, depending on the frequency of the magnetic field driving them, the two layers sitting at very different depths and made of very different material, comparing the response across several different frequencies rather than relying on just one, offered a far more sensitive way to tell the two explanations apart than any single earlier analysis had managed. An ionosphere sitting close to the surface tends to respond quickly and consistently across a wide range of driving frequencies. An ocean sitting deep beneath an insulating shell of ice responds somewhat differently depending on how rapidly the driving field changes, in ways a careful model can distinguish if it has enough data to work with. Their conclusion, while not absolute proof, leaned considerably more firmly in one direction than 2 decades of ambiguity had allowed. Models built around the ionosphere alone could not account for the observed signal across every frequency examined. Models that included a salty subsurface ocean sitting somewhere more than 100 kilometers beneath the surface fit the data noticeably better. Callisto, it now appears, very likely holds a hidden ocean of its own, sealed beneath an ice shell, thick enough that nothing happening on the surface above has any way of reaching it. That finding deepens the puzzle from earlier in this chapter rather than resolving it, and it is worth pausing on exactly why. A genuine ocean requires a source of heat sufficient to keep water liquid rather than frozen solid, and Callisto, sitting outside the gravitational rhythm that warms its 3 siblings, has no comparable source readily available. A moon that cannot fully sort its own interior, and a moon that somehow keeps a deep layer of water from freezing, despite having almost nothing pushing back against the cold, turn out to be 2 faces of the very same underlying mystery. The leading explanation involves a combination of 2 more modest factors working together rather than any single dramatic one. Radioactive elements naturally present in Callisto's rocky interior decay slowly over time, releasing a steady trickle of heat that, on its own, would not normally be enough to melt much of anything. But water mixed with dissolved salts, or with a compound like ammonia, freezes at a noticeably lower temperature than pure water does. If Callisto's interior water carries enough of either, that same modest trickle of radioactive heat, combined with the insulating effect of a thick, overlying ice shell that keeps warmth from simply escaping into space, may be just enough to keep a deep layer liquid, even without any tidal engine helping it along. If that explanation holds, it reaches well beyond Callisto alone. Tidal heating has long been treated as something close to a requirement for maintaining liquid water on a small, cold, icy body far from the sun. Callisto's apparent ocean, sitting outside any tidal rhythm at all, suggests that requirement may not be as strict as once assumed. Radioactive decay and dissolved antifreeze are not special or rare ingredients. Nearly every icy body with some rocky material mixed in carries both, in one quantity or another, whether or not it happens to orbit close enough to a giant planet to be tidally squeezed. Consider for a moment how short the current list of likely ocean worlds actually is. Europa anchors that list, supported by magnetic evidence strong enough to justify an entire dedicated spacecraft built specifically to investigate it. Ganymede appears to belong on it too, its own deep ocean inferred from a mixture of magnetic data and subtle patterns in its faint glowing atmosphere. Enceladus, a comparatively tiny moon of Saturn, confirmed its ocean directly when a passing spacecraft flew straight through plumes of water ice erupting from cracks near its south pole and sampled the material firsthand. Titan, Saturn's largest moon, better known for its surface lakes of liquid methane, appears to hold a deep water ocean as well, inferred from how the entire moon subtly flexes and rotates as it orbits, a separate hidden layer entirely from the strange liquid hydrocarbons sitting in plain view on its surface. Every single one of those confirmed or strongly suspected oceans shares one thing in common. Each of those worlds receives meaningful tidal heating, squeezed and flexed by the gravity of a nearby planet or neighboring moon, in much the same way Io, Europa, and Ganymede are squeezed and flexed by their shared rhythm around Jupiter. Tidal heating has functioned, until now, as close to a prerequisite for keeping an outer solar system ocean liquid at all. Callisto, if its ocean is real, breaks that pattern entirely. It receives no comparable tidal heating, none of the rhythmic squeezing that keeps its siblings' interiors warm. Its candidate ocean rests instead on two far quieter ingredients, present in some quantity inside nearly every icy body with a rocky core: the slow, steady decay of radioactive elements, and a freezing point lowered just enough by dissolved salts or ammonia to keep water liquid at temperatures that would otherwise freeze it solid. Neither ingredient is rare or special. Neptune's largest moon, Triton, almost certainly captured long ago from the same distant population of icy bodies that supplies comets to the outer solar system, shows signs of past geological activity, but currently receives little meaningful tidal heating of its own. Pluto, visited briefly by a spacecraft in 2015, displays surface features including a large basin of frozen nitrogen and patterns of stretching in its crust that some researchers interpret as consistent with a past or even present layer of liquid water beneath its surface. Neither world sits anywhere near the kind of gravitational rhythm that keeps Europa's ocean liquid. If Callisto's quiet combination of radioactive warmth and antifreeze chemistry is enough on its own, these distant, tidally undisturbed worlds, and quite possibly a considerable number of others scattered through the cold outer reaches of the solar system, far beyond where any telescope has yet looked closely, may be keeping oceans of their own, hidden beneath surfaces that look, from a distance, every bit as frozen and inactive as Callisto's once appeared to be. The list of places water might be quietly waiting would not simply grow by one. It would grow by however many similar bodies are scattered through the dark, which, in a region of the solar system this large and this poorly surveyed, could plausibly mean dozens or more. There is something worth sitting with in that thought before moving on. A parent answers a child's question on a porch somewhere on a clear night, pointing toward 4 faint points clustered close to a much brighter one. What are those? The answer changes with each generation that asks it. A scattering of stars to one grandparent, 4 moons to a parent a little later, once telescopes became common enough for ordinary households. A volcanic world, an icy world, a magnetic world, and a 4th one nobody quite remembers the details of, to whichever child asks next. And now, very recently, very quietly, that same overlooked 4th point may be hiding an ocean of its own, sealed away in the dark, answering to nothing and no one, simply existing, the way it has answered to nothing and no one for 4.5 billion years. The 4 points themselves have not changed across any of those conversations. Only what we know how to say about them has: a porch, a question, an answer slightly longer than the one before it. That too is a kind of inheritance, passed quietly from one generation of curious people to the next, regardless of whether any of them ever owned a telescope at all. What remains for now is uncertainty rather than confirmation. The 2025 findings strengthen the case considerably, but they do not settle it completely, and nothing currently orbiting Jupiter is equipped to measure Callisto's interior with the kind of precision needed to remove all remaining doubt. Both questions raised in this chapter, the unfinished separation of rock from ice, and the ocean that separation should not, by ordinary expectation, have been able to support, point toward the same conclusion. Whatever is happening beneath Callisto's ancient crust is stranger and considerably less settled than its quiet, battered surface ever let on. The surface told one story patiently for 4 billion years. The interior, it turns out, has been holding a second story back the entire time, one that nobody outside has yet been able to read in full. That measurement is still to come, carried by an instrument already on its way, moving slowly through the outer solar system on a path that will eventually bring it close enough to look more carefully than anyone has looked before. Some questions get answered quickly. This one will not be. Spacecraft is already in motion, somewhere in the dark between here and Jupiter, carrying instruments built specifically to test what Galileo could only gesture toward. It left Earth in April of 2023, and it is still, even now, only partway through a journey too long to rush. There is no urgency anywhere in that sentence, and there should not be. A trip of this length was never going to happen quickly. The spacecraft is not racing anything. It is simply moving steadily along a path planned years in advance, trading speed and fuel and timing against one another with a kind of patience that only a journey measured in years can really demand. Its name is JUICE, short for the Jupiter Icy Moons Explorer, built by the European Space Agency in partnership with researchers from around the world, designed from the very beginning around a single, patient purpose: to look more closely than anyone ever has at the 3 large icy moons orbiting Jupiter, Ganymede, Callisto, and Europa, and to do it slowly enough and carefully enough to finally answer questions that briefer visits could only raise. Reaching Jupiter on a reasonable budget, carrying enough fuel to eventually settle into orbit once it arrives, is not a simple matter of pointing toward the planet and going. Spacecraft headed that far out usually borrow momentum along the way, swinging past other worlds and using their gravity, almost just like a series of gentle pushes to gradually build up speed without needing engines large enough to manage the whole distance alone. JUICE's path has included a flyby of the Earth and Moon together in August of 2024, an unusual maneuver that had never been attempted quite that way before, followed by a pass close to Venus in August of 2025, each encounter bending its trajectory a little further outward, each one trading a brief, close look at a familiar world for a small additional nudge toward a much more distant one. From Earth, watching a spacecraft swing past on its way to somewhere else entirely, there would have been nothing dramatic to see. A faint point of light crossing the sky a little faster than a star, gone again within minutes, carrying instruments built for a destination still years away. More flybys of Earth are still to come, scheduled for 2026 and again in 2029, before the spacecraft finally has enough momentum to make the long final approach. Jupiter itself is not expected until 2031. 8 years of travel, total, simply to arrive, and arrival, even then, is only the beginning of the part that matters most. Once there, JUICE will spend years moving through the Jovian system, performing repeated close passes by Ganymede, Callisto, and Europa in turn, gathering data slowly, methodically, before finally settling into orbit around Ganymede itself in late 2034. The first spacecraft ever to orbit a moon other than our own. No spacecraft has done this before, anywhere around any planet. Earlier missions have orbited planets directly, or passed close to their moons during brief flybys, lasting minutes or hours before continuing on, settling into a long, stable orbit around a moon itself, rather than the planet it circles, asks for a different kind of precision, a slower and more deliberate approach, fitting for a mission whose entire purpose has been built around patience from the very beginning. Callisto sits along that route, not as the final destination, but as a stop the spacecraft will return to several times on its way toward Ganymede, using each moon's gravity to adjust its path before circling back. It is, in its own way, a familiar position for this particular world to occupy, present, visited, useful to the larger plan. Rarely the main event, and yet those Callisto flybys, almost incidental to the mission's headline purpose, are expected to deliver more detailed information about this moon than any spacecraft has gathered since Galileo left orbit 2 decades earlier. It is worth pausing on that quietly familiar pattern. A mission built primarily around 2 other moons, justified to funding agencies, and the public largely on the strength of Europa's hidden ocean and Ganymede's record-setting size and magnetic field, will still end up doing more for Callisto than any mission designed around Callisto alone has ever been given the chance to do. The attention arrives, in the end, almost as a byproduct of attention aimed somewhere else. The way a lighthouse built to guide ships toward one harbor still happens to illuminate the quiet water around it. A mission like this one does not exist by accident or purely out of curiosity about ice and rock for their own sake. Icy moons orbiting the outer planets have become some of the most closely watched targets in all of planetary science, precisely because so many of them appear to be hiding liquid water. And water, as far as anyone currently understands the conditions required for life, sits close to the center of almost every serious conversation about where else, if anywhere, life might exist. JUICE was approved, funded, designed, and finally launched within that larger context, a mission built to spend years circling worlds that might, in some quiet way nobody can yet confirm, be capable of supporting something more than empty ice and stone. JUICE carries 3 instruments especially suited to the questions this story has been quietly building toward. One measures gravity, with far greater precision than anything available in the 1990s, designed to test whether Callisto's shape truly matches the smooth, settled equilibrium scientists have long assumed when calculating that strange, in-between moment of inertia value. If the moon's shape carries some hidden asymmetry, some lingering memory of an earlier state rather than a perfect reflection of its current rotation, the entire interpretation of its partial differentiation. The careful middle ground reading, built from Galileo's older numbers, may need to be reconsidered from the ground up, the puzzle reopened rather than resolved. A second instrument, a magnetometer built specifically with this kind of question in mind, will measure the magnetic environment around Callisto with far better sensitivity than Galileo's older equipment allowed, sampling the induced signal across several different frequencies and from many different positions along multiple close approaches, where the 2025 reanalysis worked backward from decades-old data. Doing its best with measurements never designed for this exact purpose, JUICE's magnetometer will gather data built for precisely this question from the very start. A third instrument carries the most quietly dramatic possibility of all. A radar sounder designed to send signals down through the upper layers of ice on these moons and listen for whatever echoes back, the way a ship's sonar listens for whatever shapes the dark water beneath it might be hiding, searching for boundaries between different layers hidden beneath the surface. Its primary targets are Europa and Ganymede, where the boundary between ice and ocean may sit close enough to the surface for the radar to reach it directly. At Callisto, the ocean likely sits too deep for this particular instrument to detect outright, buried beneath more ice than the radar's signal can comfortably penetrate. But even a partial picture of the upper ice shell, its layering, its thickness, its internal structure, would offer something no orbital gravity measurement or magnetic signal ever could. An actual, physical look at what the crust above that possible ocean is built from, rather than an inference drawn from a distance. Buried craters, older than anything currently visible on the surface, might show up as faint structures in the radar data, an entire earlier chapter of bombardment history that the visible surface alone could never reveal. Layers of cleaner ice, alternating with darker, dustier material, might trace out a record of changing conditions across hundreds of millions of years, something closer to rings inside a very old tree than anything currently readable from photographs alone. None of this resolves anything tonight. The spacecraft carrying these instruments is still years from arrival, still tracing its long, fuel-conserving path through the inner solar system, still gathering speed from worlds it will likely never visit again. Whatever it eventually finds will not be known for the better part of a decade from now, and even then, the results will take additional time to process, to check, to publish, before anyone outside a small community of specialists hears about them at all. Picture for a moment the scale this single mission spans, set beside everything that came before it. 4 centuries between Galileo's first sighting and Galileo, the spacecraft's arrival in orbit. 3 more decades between that orbiter's last transmission and JUICE's eventual arrival at the same system. And underneath all of that, layered far beneath any human timeline, 4.5 billion years of a moon simply existing, unobserved, gathering craters in silence long before there was anyone anywhere to notice or to care. Every human effort described in this chapter, every spacecraft, every careful calculation of a gravity assist, every instrument built across years of engineering work, amounts to a single, brief flicker of attention directed at something that has been patiently waiting the entire time, with no sense of waiting at all, because waiting requires expecting something. And Callisto has never expected anything from anyone. There is a particular kind of patience this story keeps asking for, layered at every scale. Patience measured in years for a spacecraft slowly crossing the distance between Earth and Jupiter. Patience measured in decades for the long gap between Galileo's original ambiguous measurements and whatever clarity JUICE eventually provides. And underneath both of those, patience measured in billions of years, the entire span of time across which Callisto's surface has simply sat there, recording what fell on it, while every instrument capable of reading that record had not yet been imagined, let alone built. A moon that has already waited 4.5 billion years to be properly understood is not, in any meaningful sense, in a hurry now. Whatever JUICE eventually confirms or fails to confirm, the ice and the craters and whatever may be moving slowly beneath them will still be there, holding their pattern, long after the spacecraft itself has completed its work and gone quiet. For now, the questions remain open, exactly as they have remained open for as long as anyone has known to ask them. The interior is still unread. The ocean is still uncertain. Somewhere between Earth and Jupiter tonight, far past anything visible to the unaided eye, a spacecraft is moving a little further along its long, patient path, gathering the smallest possible nudge of speed from whatever world it last passed, carrying instruments that will not finish their work for years yet. It does not know it is carrying anyone's curiosity along with it. It is simply moving the way it was built to move, toward a moon that has already waited longer than anything human can easily measure, and is, by every available sign, perfectly willing to wait a little longer still. There is a particular kind of unfairness built into how attention moves through a solar system, or really through anything at all. The things that erupt get noticed. The things that crack open, or glow, or break a record get studied, funded, named in headlines, given their own dedicated missions. The things that simply hold still, keeping whatever they were given at the very beginning, tend to slip toward the edges of the conversation, mentioned last, if they are mentioned at all. It would be easy enough to call this a flaw in how we pay attention, and perhaps, in some sense, it is. But it might be closer to the truth to say it is simply how attention works for almost anyone, most of the time. We notice motion, we notice change. A world rearranging itself catches the eye in a way that a world simply persisting never quite manages to. The same pattern shows up in places that have nothing to do with moons or planets at all. A loud room draws more notice than a quiet one, regardless of which actually has more worth saying in it. A dramatic year in someone's life gets told and retold, while the long, even stretches in between, where very little seemed to happen, fade quietly out of the story altogether, even though most of any life, examined honestly, is made of exactly those stretches. Stillness asks for something different. It asks someone to look anyway, even when nothing in the moment is announcing itself, even when there is no obvious reason to expect that anything worth finding is there. It asks for the kind of attention that does not need to be earned in advance. Callisto never asked for that kind of attention. It could not have asked for anything. Whatever happened to it, the position it settled into, the heat it lost early on, the rhythm it never joined, all of that came down to physics, set in motion long before there was any audience to please or disappoint. It did not choose stillness any more than its siblings chose their own particular forms of drama. And yet, looked at now, after everything this story has gathered along the way, there is something worth sitting with in what that stillness turned out to hold. A surface old enough to remember the earliest violence of the solar system, kept whole while every louder neighbor traded its own deep past for something more immediate. An interior caught in the middle of a process its near twin somehow finished, raising a question nobody has fully answered. A possible ocean, hidden far beneath all of that quiet, existing for reasons that owe nothing to drama and everything to patience. None of it would have been there to find if Callisto had been busier. A moon that erupted, or cracked, or rearranged itself every few million years would have erased its own early record, long before anyone built an instrument capable of reading it. The very quality that pushed this world toward the edge of the conversation for 4 centuries is the same quality that left anything worth finding still intact when someone finally thought to look closely. There is a version of this thought that applies well beyond one moon orbiting one planet. Whatever in your own life has felt overlooked in any season of it, for being steady rather than striking, for staying the same instead of changing in some way easier to notice and easier to praise, might be holding more than it has ever been given credit for. Not because stillness is automatically valuable. Sometimes nothing is there. But because stillness is so rarely looked at carefully in the first place, and a thing examined for the first time, however quiet, often turns out to contain more than anyone assumed. This is not a claim that everything overlooked is secretly important. Most quiet things are simply quiet, and stay that way no matter how closely anyone looks. But the only way to find out which is to look in the first place, slowly enough and patiently enough to actually notice what is there, rather than assuming, from a distance, that nothing could be. There is a particular kind of sky that some people remember from very early in their lives, before they knew the names of anything in it. A backyard perhaps, or a window left open on a warm night, or the back seat of a car on some long drive home, looking straight up through the glass at a scattering of light that meant nothing in particular yet, because nothing had been explained. No constellations, no planets, no moons orbiting other moons. Just light scattered across the dark, taken in without any need to understand it first. That early version of looking up asked nothing of the sky, and the sky gave nothing back except its presence. It did not need to be useful. It did not need to resolve into facts or names or missions or decades-long mysteries. It was simply there, the way it had always been there, long before anyone old enough to wonder about it came along to look. There was no 4th moon yet in that kind of looking. No first or third or favorite, no ranking of any kind. Only light, undivided, asking nothing in return for being seen. Somewhere in the years between that early, wordless looking and whatever understanding came afterward, the sky stopped being only itself and started being explained, named, measured, divided into objects with histories and arguments and open questions attached to them. Something is gained in that shift, clearly. Years spent learning what any of it actually is tend to add more than they take away, but something, perhaps, is also quietly lost along the way. The capacity to look at 4 faint points beside a brighter one and feel nothing more complicated than presence without needing any of it to mean anything beyond simply being there to see. Both ways of looking, the wordless kind and the informed kind, can sit the same person, even in the same night, if the looking is unhurried enough to allow for it. Knowing that one of those 4 points is nearly the size of a planet, that another may be hiding a sea, that all 4 have been circling the same point of light for longer than anyone has existed to count the years, does not have to replace the simpler feeling of just looking up and finding something there. It can simply join it. This particular story, in the end, does not resolve into anything tidy. The interior of one quiet moon remains genuinely unknown. The ocean beneath it remains genuinely uncertain. And the larger thought about what stillness might be worth, about what gets noticed and what gets quietly passed over, does not arrive at any conclusion either, because it was never the kind of thought built to conclude. It only asks to be carried a little further, gently, the way light from somewhere very far away is still arriving, even now, without needing anyone to be awake to receive it. On a winter night in a city in northern Italy, a man once looked through a tube made of 2 lenses and noticed 4 small lights he had not expected to find. He did not know that night what any of them would become. He did not know that one would be remembered for fire, another for ice, and the possibility of something living beneath it, a third for its sheer size, and a magnetic field unlike any other moon's. He did not know that the 4th, the one he sketched with exactly the same careful hand as the other 3, would spend 4 centuries slipping quietly toward the edges of every conversation about the other 3. He simply looked, night after night, at 4 points of light that refused to behave the way the sky had always behaved before. Somewhere on some night since then, you may have done something close to the same thing, without quite meaning to. Not through a telescope of your own, necessarily. Maybe only a glance upward on an ordinary evening toward a bright point that turned out, though you had no way of knowing it at the time, to be Jupiter, with 4 small companions traveling alongside it, too faint to resolve without help, hidden in its glare, the same way they were hidden from every set of eyes that came before any telescope existed at all. You were not missing anything in that moment. The 4 moons were there, exactly as they had always been, completely indifferent to whether anyone happened to be looking closely enough to notice them. That is, in some sense, where this story keeps returning. Not to a conclusion, but to a kind of looking. A planet, a handful of faint points beside it, and someone somewhere, deciding to look a little more carefully than they strictly needed to. A farmer once might have done it, finishing a late evening's work, glancing upward out of habit rather than purpose. A scribe once might have done it, recording a single bright object's position, with no way of knowing 4 smaller companions traveled beside it. A man with a homemade telescope did it deliberately on a winter night and changed, in some quiet way, how an entire species understood its place in the order of things. None of them set out to find what they found. They simply kept looking a little longer than strictly necessary, at something most people walked past without a second glance. The 4 moons do not know which of them became famous. They do not know that one is currently being approached, slowly, by an instrument capable of finally answering questions that have sat open for decades. They do not know that another has spent 4 centuries being mentioned last, if it is mentioned at all. None of that knowledge belongs to them. It only ever belonged to whoever happened to be looking. They simply orbit. One flexing under tidal fire, one quietly hiding water beneath ice that keeps repairing itself, one generating a magnetic field deep in its own slow interior, and one, farther out than the rest, holding still, holding everything, asking for nothing in return. And the looking, it turns out, never really stopped. It simply changed shape. A homemade telescope on a winter night became spacecraft cameras, decades later, photographing the same 4 points from close enough to finally see their craters and their cracks and their faint, restless atmospheres. Spacecraft cameras became gravity measurements, magnetic field readings, careful models built from decades-old data and tested against new ones. Each generation of looking added something the last one could not quite reach, without ever finishing the job, without ever closing the question completely. Tonight, that same looking has settled, for a little while, on the 4th point, the one that asked for none of this attention and received almost none of it for as long as anyone kept count, until a surface covered entirely in craters turned out to be holding one of the most complete records of the solar system's early violence still available anywhere. until an interior caught halfway between two different outcomes turned out to be hiding a question nobody has fully answered. Until something that might be an ocean, sealed away in salt and ice and unhurried radioactive warmth, turned out to be waiting patiently for an instrument, already most of the way through its long approach. None of that has resolved tonight, and none of it needed to. The moon does not require an answer in order to keep existing. It has been existing quite comfortably without one for 4.5 billion years, and it will go on existing just as comfortably for however long it takes someone to finally bring it one. What has changed, perhaps, in the time since you first heard its name this evening, is something closer to what changed for whoever first looked up long before Galileo and saw nothing more than a single steady point of light beside a much brighter one. They were not wrong in their not knowing. They simply had not yet been asked to look a little closer. A name, once you have heard it, tends to stay. Even a quiet one, even one that took 4 centuries to be properly noticed. The next time a clear night happens to find you somewhere dark enough, and Jupiter happens to be somewhere overhead, there will be, whether you think of it consciously or not, a 4th point of light traveling alongside it that you now know a little more about than almost anyone has known. For almost all of the 4 centuries since it was first seen, you have now, whatever that is worth. The 4 points of light remain exactly where they have always been, circling the same planet they were circling on that first winter night, indifferent to documentary and dedicated missions, and quiet decades-long debates over a single number describing how concentrated a moon's mass happens to be toward its middle. They do not need any of it. They were never waiting for it. They simply continue the way they have always continued, whether or not anyone happens to be looking. Tonight, for a little while, someone was. That is close to all this story ever really had to offer. Not a discovery, finished and wrapped neatly into a conclusion, but a long, patient act of looking passed from one set of eyes to the next, across 4 centuries, arriving, eventually, here. The telescope is gone now, the original one, the wooden tube and the 2 ground lenses, long since lost to time the way most ordinary objects eventually are. The man who built it is gone too, 4 centuries gone, his sketches preserved in archives few people will ever visit. What he found is still there, still orbiting, still keeping whatever it has always kept, in the dark, at a steady distance from a planet far too bright to ever fully see past on its own.